Yeah, can you check it's okay?
Right.
Okay. So hello everyone, welcome back to the Wednesday seminars. Today we have Caroline as our guest speaker. She is a postdoc at University of Heidelberg. She completed her PhD from University of Bath and Masters from ETH Zurich. So today she will be telling us about her ongoing research. So let's welcome Caroline and the stage is all yours.
Thank you so much for organizing this talk for me. Today I would like to talk about some recent JWST results about protocluster at redshift 3, which turns out to be maturing and probably merging. But first, let me tell you a bit about where I'm from. So I am a postdoc in Heidelberg in the group of Dominika Vidic-Salek, which is shown here in the picture. She's on the left. And you actually might see in this group few faces that are familiar. A couple I've had to very skillfully Photoshop because this picture is a bit outdated, but some of you might know Bruno and Lara from here. And we also have a visitor currently from Santa Maria University, Greece, because our group is collaborating with that of Rogerio and his brother in Santa Maria. I'm also happy to report to you that if we look at only people at the PhD student level and above, then currently the dominant nationality is Brazilian with 3 people. So congratulations on taking over the group. And yeah, this is the same program that allowed me actually to come on the visit today and in the past few days. Okay, so we organized this talk here a bit at the last minute. I was originally scheduled to just give a talk on Monday about AGN stuff. So this is going to be about just a single paper in preparation. I'm trying to not repeat myself a lot. So this is rather a focused talk for a seminar, but hey, on the plus side, it's going to be shorter. So we are looking at the protocluster at redshift 3 around a red quasar. And I know this is a broad audience, so not everyone might be familiar with the term. So let's unpack it. Quasars are a type of active galactic nuclei, or AGN, which are galaxies whose supermassive black holes at their centers are currently undergoing a phase of rapid growth. So this is not really a weird type of galaxy, but rather a phase that all galaxies go through, or at least all massive galaxies. Here you see just the first image that pops up in Wikipedia of a nearby AGN, Centaurus A. And the light that you see in the center does actually not just come from the stars, but as supermassive black holes grow, they form around them this hot accretion disk of infalling gas. There's a lot of friction going on, and a lot of gravitational energy is released as the material moves inwards, which leads to an enormous amount of radiation. So much that it can in fact outshine all of the stars combined in a galaxy. And that's when we talk about the quasar. So here's an example image. And as you can see, it pretty much looks like it could be a star in our own Milky Way, even though this is a very distant source. It's just very bright. So of course, this enormous energy output puts you could imagine that it affects the galaxy around. Yeah, 2 different ways sketched in which it can do that, namely the radiation pressure and also thermal pressure might lead the AGN to drive outflows that are transporting gas outwards from the center. And on the other hand, the radiation can heat the surrounding medium, actually out to CGM scales, where it can prevent then the accretion of further gas. And these processes combined we call feedback. But I'm actually not going to talk much about this today. This is just to motivate about why my team and I were interested in studying quasars and their impact on the host galaxies. which is how the QCD program started, which is a JWST early release science program that targeted 3 luminous quasars at redshift 0.4 to 3 with spatially resolved spectra. And I'm showing you here our redshift 3 quasar. This colorful image shows the different kinematic components of the O3 emitting gas. So in the smaller panels, you can see on the top the most redshifted phase, and then on the bottom it's the most blue shifted one. You can actually make out the biconical outflow. It's between this orange blob on top and the blue blob on the bottom. We also find a starbursting region in the north of the galaxy, and the host galaxy appears to be very massive. The mass is hard to constrain because of the outshining AGN. But even with conservative estimates, we get something of the order of 10 to the 11 solar masses or more, which is absolutely huge for redshift 3. So it's a question how the system was able to grow so far. And we might find a bit more clues when we look first at the closer environment, because we also unexpectedly found 3 close companion galaxies that are spectroscopically confirmed. So they are named C1 through to C3 here. So we were wondering if this quasar might be living in a particular type of environment. The 3 companions span between them a large velocity spread of about 1,000 kilometers per second. And we also found in some existing HST imaging this sort of scattered light towards the west. Altogether, we interpreted this as evidence for us looking potentially into the core of a protocluster. And we were interested in following this up more, because dense environments are known to affect the galaxies that are part of them. At low redshift, we see fully formed virialized clusters, and it has been known for a very long time that as you move closer to the cluster core, so towards the right of this plot, the fraction of passive galaxies rapidly increases and the one of star-forming galaxies declines. So these cores are really strongly dominated by massive passive ellipticals. So in these environments, that means that galaxy evolution proceeded faster compared to the field. But that also means that some higher redshift, these would have to have been more star-forming than the field to build up all this mass. But the question is at how high of a redshift? So we can look for this at the precursors of these systems, which are protoclusters. These are sort of looser structures. They're not virialized yet, and they can exist on much larger scales, up to a few megaparsecs. And here we see a very nice compilation looking at how the star-forming activity in these systems changes with redshift. In this case, this is parameterized on the y-axis by the total star formation rate divided by the halo mass. And we see indeed that around redshift 3, the systems seem to lie above this value for the field, which is shown in gray. But there is, however, a catch with this. So a lot of these systems have been studied really by looking for line-emitting galaxies. So a lot of works have done narrowband imaging, for instance, to identify an overdensity of line and alpha emitters. And that would, by definition, miss any potential quiescent member galaxies. So if we want to try and recover the true quiescent fraction of these systems, then we need very deep, sensitive, and ideally spectroscopic observations that can show the stellar continuum. And the importance of getting sufficiently deep observations for identifying quiescent galaxies has been highlighted a lot in recent years, with JWST recovering a much higher number density of quiescent galaxies at high redshift than previously thought. So you can see that with the increase in sensitivity, the number density at high redshifts has increased by almost an order of magnitude. I should note a lot of these are not spectroscopically confirmed yet, but candidates of quenched galaxies from photometric surveys. So the numbers could still change a bit, but I think it will in any way be there will in any way be more quenched systems than we originally thought, and this poses a challenge to explain how they have evolved so fast to already be quenched by redshift 3, 4, and even more. So could environment potentially play a role in this? Simulations seem to suggest that yes, passive galaxies in elasticity and G at least seem to inhabit predominantly dense environments where they experience more HN feedback. Here we can see that the quiescent galaxies spend more time in massive halos, and that just means they live in halos that formed earlier and also grew more rapidly, so in overdensities. Okay, but back to our field. So we have spectra really only for a very small field of view. This is 3 by 3 arc seconds. Of the wider field, we have a couple of HST images, but photometry in 2 bands is not enough to derive reliable redshifts. So how can we study whether there is a protocluster around the system? We can use the technique of slitless spectroscopy, and for that we can use the NIRISS instrument aboard JWST. So usually if you know the locations of your galaxies that you suspect to be at a similar redshift, what you could do is to point at each single galaxy, place an aperture, maybe a slit, to get the spectrum for a single galaxy and block out the light of any other contaminating sources around. What we do here instead is to just let the light from the full field fall onto a spectral grating, which then leads to these grism images in the middle and right, where one axis is both spatial and spectral. So here in the center, we have the spectrum of the quasar. Then the spectrum next to it will correspond to this source here in the direct image, and so forth. Each of these lines here is spectrum of a different galaxy. Of course, in a dense field, you might have several spectra that overlap and contaminate each other. So to mitigate that, we don't just have one spectral grating, but we also have one in the orthogonal direction to hope that in one of these cases, there might not be so much contamination. Okay, so we can now look at extracting a single spectrum, for instance, that of the quasar. Here it is. And you can see it is very low spectral resolution, but we do see lines that we were looking for, like O3 and H beta, also O2, and some neon lines in there. And for the quasar, we actually had ground-based data from GENIUS that is covering these spectral features as well. And oh, I should mention, sorry, that's our GRISM observations on the left only have observations in 2 bands, one around 1.5 micron, the other around 2 micron. And towards the edges of these bands here, the signal is not reliable. At the edge, you have a lot of noise. So we should look more at the lines that fall in the middle of the. Okay, but what I was going to say is in the GENIUS spectrum, we do see that the ratio of O3 to H beta and also O2 to neon 3 looks similar, so that is good news. We can now use the spectra of the full field to search for more systems that fall at the same redshift, and here I'm showing a few of them. So I've tried to pick representative ones, and the gray points in the back corresponds to all of the data points from the individual pixels, whereas the real extracted 1D spectrum is then shown in blue, which is a median value. And then I have just very roughly fitted these with just a single galaxy template shown in light blue. But this is really mostly to get redshifts. On the left, you can see then the posterior distribution of the redshifts that we get. So they are actually quite robust. And yeah, on the right, just some photometric images. And overall, we find 18 galaxies in the field around our quasar. This field is, by the way, about 1 megaparsec by 1 megaparsec wide. And the galaxies are here color-coded according to their redshift, which you can interpret as a velocity offset from the quasar, or alternatively as a spatial separation along the line of sight. We cannot really distinguish between the two. So maybe if you don't work at these redshifts, you might not immediately know, is 18 galaxies a lot? Is it not? So let's see what we would expect from the galaxy stellar mass function. We don't have great estimates, mass estimates for our galaxies, but if I use some mass to light ratio, I find that our galaxies are more or less exceeding 10 to the 9 solar masses. So we can integrate the galaxy stellar mass function from there. And then we find that within the volume probe by our observations, there should be only a bit over 1 galaxy in the field. So this leaves us with a large overdensity of a factor 15. And this is actually quite rare in the literature. So from doing a deep literature search, I was only able to find 6 other systems with overdensity factors quoted to be a factor 10 or more. I'm listing them below. Okay, so I've showed you some line emitters, but in the motivation, I also said we are interested in whether we see any quiescent galaxies. So do we find them? Drum roll. Yes, we find a couple. Here you can see they show very strong 4,000 angstrom breaks, also Balmer breaks. And this is also, again, not something that has so far been studied so much. In the literature, I found, again, only 6 different papers that have claimed at least 1 passive galaxies in a protocluster beyond redshift 2. So one reason I was very happy to come here is that there is a lot of expertise on fitting stellar populations. And Lais in Bertemes' group was very kind and had a quick first try at fitting these low-resolution spectra with the starlight code. And this first try seems to suggest that both galaxies are about a giga-year old. And moreover, there was no obvious evidence for stellar populations younger than half a giga-year. But as I said, this was just a quick fit with assuming lots of default values. So Lais has actually taught me now how to use the code. Thank you. So we can try playing with the assumptions a bit, also perturbing my very messy spectrum within the observational uncertainties to see how robust these results are. So I was saying, this is a very dense system, and you might not immediately know among such a high number of galaxies, is it that unusual to find 2 quiescent galaxies? So let's have a look at the passive fraction in the field at redshift 3. This is supposed to be about 5% of all galaxies that are passive for a given mass threshold above 10 to the 9.5 solar masses. If I apply that same mass cutoff to our cluster, then I am left with 13 galaxies, including the two passives, which suggests a quiescent fraction that is actually a factor 3 higher than the field. So this seems to be consistent with a picture where protocluster environments can be efficient sites for rapidly evolving and quenching galaxies.
So you are saying that these two galaxies that you fitted the spectrum
Yeah.
are quiescent
Yes.
at 1 gigayear.
Yes. No, so the mass-weighted and light-weighted ages were both about 1 gigayear, and then
And this
there
would
was-
be passive on your evaluation.
yeah, I mean, I don't want to make too strong statements
Yeah,
right now, but if we do a lot of tests and find that we never see recover any populations younger than half a gigayear, then I would say that these are actually quenched and not just mini quenched or lulling, because they have stayed quenched then for.
So, and the others, you said that there are 13, right? So you can get.
Oh, no, that was just so all other galaxies other than these two, so lines and.
Transitional lines, and you don't have such a continuous.
No, the others look more or less just like the spectra that I showed here. They are quite representative. We do usually detect the continuum, but not at very high signal to noise. And the sample of 13 galaxies was just that I have 13 galaxies with my best mass estimates exceeding 10 to the 9 solar masses, which was the mass cutoff that the study on the left uses to determine the passive fraction. So to do a fair comparison, I just applied that same cutoff to my sample. But my masses are also super uncertain, like the mass to light ratio can vary by about an order of magnitude at that redshift.
Yeah, I don't understand very well how to determine if it's passive or not non-passive. You are showing these two, right? So, but the rest I don't know. I didn't get. I missed something.
Sorry, yes. So the fact that they are passive, I attribute this to the presence of this very strong 4,000 angstrom break, also Balmer break, and then no H beta emission, which we should see around 2 micron there. In fact, we see slight H beta absorption. So from the absence of H beta, there is no evidence for ongoing star formation.
Would be just that the emission is filling in the absorption, so could be some residual star formation still.
Sorry, can you repeat?
You just said that the H beta absorption is very weak, right? So it could be that there is a combination of absorption and emission, and the emission is filling in the absorption. So it could be still some residual star formation.
Yeah, that is true. And also we cannot exclude the presence of obscured star formation.
Yeah, the continuum that you showed looked like a whole starburst galaxy. But I was just curious because the absorption lines are not as deep as the model.
No, but the model needs to be degraded because the resolution is.
Okay, it was not degraded.
No, we have not done that. It's just a very first try. We need to change the complete phase to degrade the spectral resolution of the red lines to be as the black ones. It's 2000 versus 200. And this might change a lot.
Okay.
Right, it's just on the continuum side is more or less okay, but on the lines, no.
Okay, no, I just had this in mind because the BPXF, you need to input the resolution of the data. So that it degrades.
It's the way around, like you do it with the base first, then you say, okay.
Yeah, but the observations that you see on the spectrum look like a post-starburst.
Yes, it's like, it's more a matter of when you degrade the resolution, the red lines, they will get a little bit broader and less deep, then they will more or less fit the black ones.
Yeah, the spectral resolution is very low. R is about 150 for my observed spectra.
150.
Yes,
Okay, because it is Greece, right?
exactly. Yeah, we were really just trying to find a cheap
Okay.
way to get spectra and
Yeah.
therefore redshifts for many galaxies in this large
Okay.
field of view.
Mhm.
Yeah, but just looking at this, I would say if there is a star formation, it is residual.
Yeah,
It's not strong.
Okay.
it's really a big possibility.
All right. So, okay, we have two mature galaxies, potentially with some residual star formation, but not much. So does that mean that our entire system is somewhat uniquely maturing? Well, we can revisit a plot that I have showed earlier. So this is showing the redshift evolution of the star formation rates summed up and then normalized by the halo mass. And if I put our system on this, then it should fall somewhere in this red bar. So it is appears to be either consistent with other protoclusters or somewhat less star forming. But the uncertainties are large. For example, I'm deriving the star formation rate from H beta without knowing much about the dust. So I'm just assuming a range of dust extinction values. And the star formation rate of the central quasar is very hard to determine. But because it is a starburst, it can actually contribute as much as a third to the total star formation of the full protocluster. The halo mass itself, we also don't have a good way of measuring it. Usually people use the velocity dispersion and assume virial equilibrium, but by definition, protoclusters are not virialized, so this can only give an upper limit. So the other thing I did was to use the stellar mass halo mass relation, which comes with different uncertainties, like the relation has a lot of scatter, but also my stellar masses are have uncertainties of like an order of magnitude due to assumptions of the mass to light ratio. And also our observations might not probe the full protocluster. It could also extend beyond our field of view of 1 by 1 megaparsec. But anyway, our best guess is the halo mass is something like 10 to the 13 solar masses or exceeding it, which simulations suggest could mean that it evolves into one of the most massive coma-like clusters that we see by low redshift. Okay, with all of this talk on galaxy evolution, I'm not forgetting about the AGN. So how can we say something about the AGN fraction? Well, at low redshift, we would use the BPT diagram, which is contrasting O3 over H beta to N2 over H alpha, because these line ratios trace the physical conditions of the gas and can distinguish between different ionizing sources. So we have this sort of dividing line distinguishing between AGN and non-AGN. But the line ratios are not just sensitive to the ionization parameter and slope of the irrigating ionizing field, but also to the metallicity, which means at high redshift, we have to adjust this dividing line. We are then left with the red line that you see on the right. And then there's, however, the big problem that our observations don't cover N2 over H alpha. So the only thing we can do really is to search for the most extreme galaxies, which have such a high O3 over H beta that it would not be easy to explain with star formation alone. And then we end up with these two AGN candidates that you can see on the left, which tentatively suggests an enhanced AGN fraction by about a factor 2, which might not seem like that much, but again, we're only targeting the most extreme systems here. Okay, finally, I want to discuss also the structure of the protocluster. Here you can see it on 3D as viewed from the side on. So the longest axis here is corresponding to the velocity offsets derived from the redshift. As I said before, they might also be interpreted as spatial separation along the line of sight. And the colors here are just to show which data points should come out of the screen versus being pushed in. They don't have any other physical meaning. So maybe you can see this kind of jump where all of the northern targets seem to fall at negative velocities. And all of the southern targets are clustered around the quasar or at positive velocity offsets. So this step-like, because of this step-like structure, I am proposing to nickname this the step protocluster. It's the first time I'm trying to nickname anything, and I've just sent out a paper draft to collaborators, so I'll see how they react. Anyway, the bigger point, other than the nickname I want to make, is that the kinematics are actually quite unusual. So we have a very broad velocity distribution spanning about 3,000 kilometers per second. And we have evidence for these two substructures that are separated in their centers by also more than 1,000 kilometers per second. We also find in the red subgroup a very dense line of sight where within a search radius of 70 kiloparsec, we find 7 galaxies that between them span 850 kilometers per second. And it turns out this is actually really difficult to explain with just a single halo. Why am I saying this? Because while the system is very rare, we did manage to find one other published system with similar kinematic peculiarities, which is the spiderweb structure at redshift 2.2. It also has a very broad velocity dispersion. It also shows these two subgroups, which you can see here by the blue versus red contours. And they are separated also by a large velocity spread. And they have also a very dense line of sight in the red group, reaching like 1,000 kilometers per second. So it seems to be a good analog to the system that we're studying. And what the authors did here was to use the Millennium simulation and search for any dark matter halos that might be able to explain these kinematic properties. And they found that no single halo was able to do it very well. However, there was also a merger of two dark matter halos at that time slice. And here you can see what happens to the kinematics. So on the top, we see the velocity difference between the two substructures. And the curve you have to look at is the black one that shows the direction along the line of sight. The other two curves are the other two spatial directions. And you can see that this velocity difference and also the velocity dispersions strongly peak at the first pass of the merger. We have another peak in the case of the velocity dispersion at the second pass. And the numbers then actually match quite well the observations. So this does seem to be the best explanation so far to explain the observations in the the spiderweb structure, and then by analogy also our step system. And yeah, those were the main points I wanted to make. So let me recap. We found this protocluster at redshift 3 kind of by accident because we wanted to study a quasar. It turns out to be really dense, really massive, with a halo mass of like 10 to the 13 or more. Which means it could potentially evolve into one of the most massive clusters we see at redshift 0. And it has both two quiescent galaxies, all with residual star formation, but also then the central quasar, which is a starburst. So this highlights that the structure is actually at a transitional stage. And it might currently be experiencing a turnover in star formation. And then finally, it seems that according to simulations, a merger of two dark matter halos might be the best possible explanation for the observed kinematics and substructure. So all in all, what have we learned? Well, it is just a single system, but it appears to be consistent with a scenario where protoclusters are good, efficient ways to form more quiescent galaxies in high redshifts, and this could potentially help us to understand the abundance of mature galaxies at high redshifts that JWST has uncovered. But of course, there's a lot more to be made. I'm looking forward to seeing more deep observations that can probe the stellar continuum, and I'm excited to see how the field evolves. Thank you for your attention.
Thank you, Caroline. So any questions?
Okay.
Yes, please.
The image you showed of the system.
This one?
No, the image.
Yeah.
So you are saying that there are 13 galaxies, because that beautiful image, the first one, it's not this one, right?
Oh, the beautiful,
This one.
colorful image here. Yes, that is.
This is only the central part of the cluster, or
Exactly.
everything is in there? I didn't get this.
Sorry. So this zoom in here is only the central part. This is 3 by 3 arcseconds for which we have near-spec IFU data. So this is showing you here the quasar. And then you see one of the close quasar companions here. We have 2 other spectroscopic companions, which you don't see because of the color stretch here, but they are also spectroscopically confirmed and detected in lines and continuum. But yeah, this is the very center of the structure. So this is like 20 by 20 kiloparsec.
And you are looking at the 1 by 1 megaparsec.
Exactly, yeah.
Oh, okay. And so the data for the 1 by 1 megaparsecs is what? Is also from JWST?
Yes, that is from the NIRISS instruments on JWST. So that provides wide field slitless spectroscopy.
Oh, okay. I understood. Thank you.
Yeah. By the way, here in this image, this star, it's hard to see here on the screen, but it actually has like a small red. Here, yeah, a small red rectangle, sorry, square in the middle. That is the extent of the near-spec observation, so you can compare it more directly to the field of view from the NIRISS follow-up.
Any more questions? Yes.
A question about the 18 members that find within the slitless spectroscopy fields of James Webb. Okay, it's about 1 megaparsec squared wide.
Yeah.
But it seems that your members are 20 megaparsecs apart in depth, because you're selecting members with a velocity difference of about 2,000 kilometers per second from the center of the cluster. Why do you have this choice? Are you just presuming that peculiar velocities allow you to, make a redshift of the members so wide? It seems to be a bit too much in depth for the cluster members.
So my approach was to just look for all the galaxies I could find within a given redshift cuts. I think it was like 2.8 to 3.1. The quasar is in the middle of it. And then we found that, so this redshift range was broader than the 2,000 kilometers per second, which are 3,000 kilometers per second that the structure spans. But because the coverage is kind of continuous along the velocity axis, we therefore assume that the stars in fact belong to all the same structure. We did also we do make a comparison also to another protocluster with similar substructure but a bit farther away, where the simulations show that it's not expected to evolve into a single structure by redshift 0. But for that, we find that if you plot the velocity distribution, that the peaks are really much further apart than what we see in this system. So yeah,
you expect this to, from redshift 3 to redshift 0, this is likely to virialize into a single
yes,
structure.
that is what we so we didn't do the comparison to simulations ourselves, but what from the comparison to the spiderweb protocluster, which then did compare it to the Millennium simulation, suggests.
So regarding the DPT show, for the two agent candidates, something that could put them high is very low metallicity, like gas would put them there. So they are quite close to the limit, let's say, to be considered agents, because they lie like on the top of this line. A little bit playing with metallicity can put them.
But would you
Yeah,
expect to find such a low metallicity in a massive galaxy? I don't think so.
Yeah,
Not at redshift 3.
It-
Could be, but
Yeah.
I won't bet on it.
So we do have both the O2 and O3 line, which sometimes is used as a very rough estimate of metallicities. And from that, we do seem, if we then compare that with O3 over H beta in a different diagnostic, they do seem to fall into the AGN regime, but then most of our protocluster does, so I don't really know how much this tells us.
It's hard, like,
Yeah.
it's very good to ask for a new proposal, to ask for like the sleep spectroscopy of the sources on JWST.
Yeah, I think that could be a really nice idea, since now we know the location of the targets. Here our aim was just get redshifts, worry about anything else later.
Really.
Could you use another diagnostic to find an agent? I'm just picking up on what he was saying. To use another diagnostic that you get like from SED fitting or something like that, from photometry, not spectroscopy.
So we unfortunately do not have a lot of photometric coverage in this field. We have the two HST images, but this is just 2 bands.
So it's not
I
like
did check.
candles field or whatever.
No. In terms of other AGN selection methods, the quasar is luminous enough and radio detected, but I think any of the other galaxies might be too faint for that. I also didn't find any obvious X-ray detection.
Perhaps you mentioned this, but how do these results compare with cosmological simulations of protocluster formation at this theta about 3? Is there any contradiction or no? I mean, cosmological simulations predict these kind of systems at this redshift. I mean, a quasar with these quiescent galaxies.
I don't know, that is a good question. Yeah, so we do have a prediction from simulations about quiescent galaxies at high redshifts. living preferentially in dense environments, and they also showed a lot of correlation with the cumulative AGN impact. But I am not sure if the simulation, so I didn't search if there are commonly systems that have both an active quasar and then passive galaxies. So unfortunately, I don't know. Okay.
Okay, then let's end then.
Very nice.
Thank you.
The results, they are so cool.